Hey guys, welcome back to chapter 13. In this video, we're going to talk about the second shortcut to solving these um, problems that have the quadratic nature to them. So the last shortcut we're going to talk about is something called simplifying approximations, or x is small. So first, I'm going to introduce the concept of what a simplifying approximation is, so just kind of give you some background information. And then we'll dive into an example together. So simplifying approximation is going to take out the quadratic nature of these equations by kind of eliminating one portion of the equation. So we can make an approximation that simplifies the calculations without any significant loss of accuracy. So here we see an ice table. It's filled out. We're ready to plug it into the K equation. And so I'm going to plug it into the K equation real quick. Okay, so we're back to that like A, plus A creates 2B. Here's our ice table filled out at equilibrium. Then we have K equals products on the top, so 2x squared, reactants on the bottom, 1 minus x on the bottom. Okay? So not a perfect square, right? We have a squared value on the top, but we don't have a squared value on the bottom. But with that squared value present and this 1 minus x on the bottom, this is going to turn into a quadratic problem. What the simplifying approximation does is it assumes that this x right here is going to be significantly smaller than the value of 1. So if I can assume that this x value is significantly smaller than 1, what we'll say is that by subtracting by that number, it doesn't really change the answer that much. Okay? So for example, what if we end up determining that x equals 0.0002? Okay. Is there really a significant difference between the number 1 being down here at the bottom or the number 1 minus 0.0002? So if I did 1 minus 0.0002, that would be 0.9998. Is there really a difference between the number 1 and the number 0.099998? I don't think there is, right? So what this x is small approximation does is it says, I think this x that's being subtracted or added is significantly small enough that's not going to affect the answer if I ignore it. So in simplifying approximations, what we do is we can ignore any x values that are being added or subtracted. So this is where it gets the name x is small. We're assuming x is so small that we can just ignore it altogether. Now let me address this x up here. So if I multiply or divide by an extremely small number, does that significantly change the value? Yeah, it does. So 2 times 0.0002 is a significantly different number. So I cannot ignore x's that are being multiplied or divided, but I can ignore x's that are being added and subtracted. Well, at what point is x small enough for us to ignore it? So there are some rules and regulations to this. So we have to fit this kind of validation, this check, okay? So to make sure that x is in fact small enough to not affect the overall outcome, we will take x, whatever that value ends up being, we're going to divide it by whatever number it was added or subtracted from, and then we're going to make sure that that's less than 5%. Okay, so let me rewrite what we had going on over here. So in this scenario, let's say we solve this equation, we determine that x is 0.0002. Make sure that that is in fact small enough to ignore it. So what we would do is we would take our x value, so x is 0.0002. We would divide that by the number that we would have added or subtracted it from. So we're going to divide that by 1. And then we're going to multiply it by 100 to make it a percentage. So when I plug this into my calculator, I got 0.0002 divided by 1. And then I multiply that by 100 to make it a percentage. And we see that this is 0.02%. So what that tells me is as long as this validation is less than 5%, and it's significantly less, as long as it's less than 5%, this x is small is valid. It's an okay approximation to make. And it was a good way to solve this problem. It was a good shortcut to take. An example. I just threw a lot at you. So let's just dive into an example and work through one together. And hopefully this will make a little bit more sense. So here's our problem. A reaction vessel initially contains 0.025 molar H2S. Find the equilibrium concentrations of hydrogen and sulfur. If you want to go ahead and try this one, you can get to the K equation. So fill the table out with x's, put those values into the K equation, and then stop. And I'll catch up with you at that point. All right, so we talks about initially here, so we know it's going to be an ice table. Reactants and products on top, so reactant, product. All right, and it gives us the initial concentration of our reactant. No mention of our products, so we can assume those are 0. We don't have any equilibrium values, so this is the best I can do. Now I'm going to have to start filling it in with x's. So I know that my product is going to go up. Products are going to increase. That's the only... Try this again. Products are going to increase because that's the only way for them to go. Reactant is going to decrease. So if we're making products, the only way for the reactant is to go down. And then this one is going to go up by a value of 2x because of that coefficient. This one's going to go up by a value of x. This one's going to go down by a value of 2x. So this is turning into a pretty hot mess. So at equilibrium, we've got 0.025 minus 2x. we've got 2x, and we have x. Now we're going to plug this into our k equation. So we're given the value for k. So we've got 1.67 times 10 to the negative 7th equals, and we've got this hot mess over here. So products over reactants. So products are going to be 2x squared times x, and reactants are going to be 0.025 minus 2x, and that is squared. So this looks really, really, really messy. It's not a perfect square, okay? So I do have a squared on top, a squared on bottom, but I also have this x right here that is not squared, so I cannot do perfect square. But I can try x's small approximation. So x's small approximation tells us that anytime an x is being added or subtracted, we can assume that that x is really, really small, and it's not actually going to affect the outcome. So in this case, I am going to ignore this x value that's being subtracted. So I can only ignore x's that are being added or subtracted. That's the only one I can ignore. If I were to ignore that or get rid of it, let's clean this equation up. So now we've got 1.67 times 10 to the negative 7th. On top, we have 2x squared on the and x. On the bottom, we have 0.025 squared. So by ignoring that x, it gets rid of the quadraticness of this equation, and it's a little bit easier to solve. Okay. I'm going to click ahead a couple slides, and we're going to solve this together. All right, so we've got 1.67 times 10 to the negative 7th equals 2x squared times x over 0.025 squared. All right, so I'm right-hand side, so let me just rewrite this left-hand side. On the bottom, I've got 0.025 squared, so 0.025 squared gives me 6.25 times 10 to the negative 4th. And then on the top, this 2x squared, I'm going to distribute that through. So we've got 4, so 2 squared is 4. X squared is x squared. And then we still have that x that we're multiplying. When we multiply x's together, we essentially add the exponents. So I have x squared times x with that exponent of 1. So if I add these two together, what happens is we get 4x cubed on the top. Now we just need to solve for x. So the first thing I'm going to do is get this guy out of the denominator. So I'm going to multiply by 6.25 times 10 to the negative 4th. Cancels, cancels. Whatever I do to the right side, I also have to do to the left side. So we're also going to multiply by 6.25 times 10 to the negative 4th. So multiplying these two numbers together. So now I have on the right-hand side 4x cubed. On the left-hand side, I've got 1.67 times 10 to the negative 7th times 6.25 times 10 to the negative fourth. And over here we get 1.04 times 10 to the negative 10. We're trying to get x by itself, so the next thing I'm going to do is divide by 4. So divide by 4. 4 on top, 4 on bottom, they cancel. Whatever I do to the left side, I also have to do to the right side. So now we have 1.04 times 10 to the negative 10th divided by 4. 0.6 times 10 to the negative 11th equals x cubed. And now to finish solving, we're going to take the cubed root. And after we do that, we'll have just x on this side. If you don't know how to do the cubed root, you can Google a YouTube video on how to do cubed root on your specific calculator. It is something that's going to come up again, so I definitely would take the time to do that. But I'm going to type into my calculator the cubed root of 2.6 times 10 to the negative 11. And the answer that it spits out is 2.96 times 10 to the negative 4. So, still a pretty significant algebra problem, but not quadratic. So that's great. That's good. We wanted to mitigate that. Okay. So what is x? What do we do with this x value? Okay, so let's first go back to what it's asking us for. It's asking us to find the equilibrium concentrations of hydrogen and sulfur. So, equilibrium, the concentration of sulfur is just x. At equilibrium, the concentration of hydrogen is 2x. So that's ultimately what it's asking for. So here's what it's asking for. Concentration of sulfur at equilibrium is 2.96 times 10 to the negative 4th molar. Concentration of hydrogen at equilibrium is that value times 2. So 5.92 times 10 to the negative 4th molar. But before we get too terribly far into the answer, we want to make sure that our x is small approximation is valid. Was that a good approximation to make? Was it okay that we ignored that x value? So to make sure that the approximation is valid, we're going to take our x value. So x was 2.96 times 10 to the negative 4. And we're going to divide that by the number that it was being subtracted from. Okay. So we'll go back to where we ignored it. So it was going to be subtracted from 0.025. So on the bottom of this is going to be the number that it was supposed to be subtracted from, which was 0.025. Now we're going to multiply this value by 100 to get a percentage. So we're going to take 2.96 times 10 to the negative 4th divided by 0.025 times 100 to get a percentage. And this value is 1.18%. That value is less than 5%. So this tells me that the x's small approximation was a valid approximation. It tells me that subtracting by 2.96 times 10 to the negative fourth would not have significantly changed the problem or the outcome of the problem. So it was okay to ignore that to make our lives a little bit easier. So that's the x's small approximation. If you do these x's small approximations, I do need to see a validation, okay? So we don't just get to take x's out of the problem and not have any explanation or of what we did and why we did it. So if you do these x's small approximations, I do need to see a validation out to the side. What if it fails validation? So what if it's more than 5%? Well, then you're going to have to go to the quadratic. Okay, then you're going to have to do the quadratic formula. So this will work a large majority of the time, but if it doesn't, then you can go back to that trusty quadratic. I hope you guys found this helpful.